Okay, well, so just go out in the street and buy a translator. That's easy, right? Not easy. You can't find them. Okay, a single application is made out of multiple technologies. We got languages, we got job control, we got schedulers, we got databases, we got interfaces, we got security management. We have all this stuff. And this tool has to know about all these things, or it's not going to succeed. So you're not going to find one off the shelf, right? All right, so you also have a problem with the target technology. Well, I want to move to C#, I want to use a Java, I want to do a Java backend, and I want to use DB2 as my database, and I want to communicate using FTP. So the output technology is unique. The input technology is unique. The only way you're going to find a translator like that is to construct it. Okay, if you can't construct it fast, it doesn't matter. You're not going to get it. Okay, so you need a methodology for constructing them fast. That's the kind of engine the DMS is. It makes it possible for us to construct those things relatively fast. I want to say relative in the sense it's not tomorrow. It takes us a while to do that, but it's a small, efficient team. Okay. So here's a legacy system. Okay. Any airplane you see that flies is 25 years old. Okay, including the software that runs it. Built with the best technologies you could get 25 years ago. Guess what? They're legacy systems. They have all the same problems you guys have in this room. Okay, including maybe worse. Okay, like the programmers are dead. Okay, I can't buy a development system anymore. Okay, I got a couple in the refrigerator and they're dying. Okay, but they're critical. Okay, this one's critical to the Defense Department for the U.S. Okay, it has 250 16-bit state-of-the-art 1973 microprocessors in it. Okay, these are great processors for 1973. Okay, but they're too small for today. They don't handle the increment and functionality the Defense Department wants. They're not fast enough to do the arithmetic. Okay, they want to replace all those microprocessors with like a Power PC running in C. Real simple, right? Okay, not real simple. There's 250 programs sitting in that thing, and they all have to be converted. Okay, well, this was done by Northrop Grumman. They came to us and said, we have this problem. We have all the 16-bit software. Okay, we don't know what it does. We forgot. The programmers are retired and gone. But you know, if it doesn't run right when you put it back in the airplane, we lose a billion-dollar airplane. This is not a happy event for the treasurer. Okay, so they have, as an example, one of the applications that they dealt with is 350,000 lines of mission code. This is basically the thing that runs the airplane and flies it from here to Baghdad, drops a bomb and comes home, and the pilot just sits in a lawn chair and waits. Okay. They need more space and speed. Okay, they forgot what it did. Okay, they tried all those other techniques that I talked about, all the manual conversions. They didn't farm it out to Mumbai. They weren't real keen on that idea. Okay, but they basically tried those other techniques, and after trying twice and failing completely, they came to us and said, you guys look different. We know what we're doing now doesn't work. Let's try a different way. Can you do this? Okay, well, we did it for them. Okay, so we built them an engine to carry off the migration. It was custom to their particular piece of hardware and dealt with the fact they had funny, weird floating point in it. This is where the custom translator stuff has come in. It took us about 12 months to implement that translator with a very small team. Right, we had 2 guys on it for that 12 months. Okay, we carried off transformations. I'll show you what they look like in a moment. Okay, 100% automated conversion in this case. Now, I don't want to say that that's easy to do. That was very hard to do. Usually we arrive at systems for migrations that do 95 to 98%. Okay, whether you get to the last 2% is really a matter of sort of how much engineering energy do you want to invest. There's a point where it's just easier to finish it by hand. Okay, in this case, it's like, we want this perfect because we don't want to lose the airplane. Okay, so they pushed hard on us. We built them 100% translation. They're now starting to install them in the B2. Okay, they actually had great tests. Okay, the system functionality test. How do you know my B2 doesn't die? The answer is there's a hangar in Oklahoma. It thinks it's a B2, but it doesn't get off the ground. Okay, and so they've actually taken the software and flown it in the hangar. Okay, and they have large system tests that verify that things seem okay. So this is a case where Northrop Grumman acted as the system integrator, and they had good tests. So it was sort of an ideal circumstance. Still a tough problem. One last issue with this one. It's top secret code. We were never allowed to see it. So we had to build the translator, throw it over the wall to them. They ran it. Didn't quite work every time. Okay, they'd send back some complaints. We adjust it, repeat back and forth. About 6 cycles of that to get to a working translator. Okay. Whoa, this is ugly stuff. Okay, I want to give you a sense of what the core of the engine looks like. Okay. The key idea behind DMS, the transformation box, is the basis of mathematics. Mathematics says that this formula is equivalent to that formula. Remember the equal sign from algebra? This formula is equal to that formula. That's the entire core technology for DMS. If you see this, replace it by that. The difference is that algebra systems do that on algebraic formulas in math. We do it on program pieces. So this funny looking thing here, in this patch, is a for statement written in jovial with placeholders for the pieces of a jovial state. So it's got a for and a loop control variable and a first formula and a second formula and a statement. So if you have a for statement, it looks like this. If you see this in Jovial, replace it by this in C. How do we know that? Well, source domain is Jovial, target domain is C. These are actually things, this is a transformation actually out of this migration tool. So replace this thing by those things, and you can see the loop control thing gets copied through here. Okay, and the statement gets copied through here, and some other rules are applied to the statement and loop control to translate them. So that's a single rule. That's kind of what it looks like. You can kind of understand what that looks like, I hope. Sort of clear what's there? Okay, well, given there's two translation rules here, okay, I'm going to explain the other one. Okay, if I take those two translation rules and I run them over this piece of Jovial code, okay, it applies those two transformations and I get this piece of C code. Okay, completely automatically. Now, that's easy for two transforms, that's easy to see. What makes the problem of building a migration tool hard is you have to translate the manual. Everything in the language reference manual has to be addressed. If it says multiply in the context of an array subscript works like this, there's probably going to be a language translation rule in there for that. So you need a lot of rules, 2,500 rules. And that's kind of where the engineering effort goes on our part. That's where custom smart guys get involved, okay, to build the rule set. All right, and those rules are completely specific to the Jovial to C translation that this particular customer wanted. Right. Okay, now there's a question as to why this process is reliable. You want to do this, you want to be scared to death of the answer. You need to have some convincing argument as to why you can get to an answer that works. Okay? And I'm going to put people in the system and they make mistakes. I'm screwed. No, I'm not screwed. Okay? I win because we have an iterative scheme. If you have a translator engine and you've got a set of transforms that you've built that you think are sort of right, it's cheap to run the translator. Okay? I don't care if it's going to run on 20 million lines. Okay? It takes a week of CPU time. So what? That's cheap. So you run all that. Okay? You get an answer. The answer may or may not be right. You need good tests. Okay, that's another topic. Okay, but assuming you have tests, you decide whether you think the answer is right or not. If the answer is not right, you go back and adjust the rules and try it again. That's not your production system until somebody says they all work. And so this happens completely offline with respect to the currently developing application system. Secondly, this is the application system. We don't care if it changes. Okay, as long as you stay using the same basic technology. So if it's evolving over time as we're building these things, it doesn't have any impact on this process. So we can repeat this process until we get it right. And then when it's right, then you can have some real faith in the answer. Okay, now what you want when you do a migration are two things. You want out of the old technology. But what you don't want is to fall into a new bungee trap, right? You want into some technology you can live with, something you can maintain. And so when you do the conversion, you don't want just the dumbest translation you get. You want translation you can live with. Okay, so this is an example from just an unnamed vendor, okay, for natural code. Okay, and what they do is they take in this piece of natural code and they produce this output. And it works. Okay, but it's not really kind of what you'd expect. Okay, it has a whole bunch of interesting flaws. Okay, it uses nested ifs instead of switches. Okay, it does lousy comparisons, inefficient comparisons. It's got natural idioms. And there's a thing called fetch here. Where's fetch? Fetch. There's a thing called fetch here. This is a natural idea. What on earth is it doing in in Java code? Okay, what they do is they copy natural libraries. So in order to maintain this piece of code, okay, your application engineer not only has to know Java, but he has to kind of understand how natural was put together, or it won't make any sense at all. You will not be able to maintain this piece of code. Okay, so you will succeed in the small and fail in the big. Okay, that's a database call. Everybody knows what it says, right? Hick. Okay, what you really want is a translation looks something like this. Okay, this is the kind of thing our tools would produce. Okay, where you basically have efficient constructs, it's relatively readable code, you can see the database call there directly. This is a transaction commit, it says commit. How hard is that to understand? Okay, we get that effect by translating sort of low-level concepts and then following follow-up optimizations to clean things up, okay, to make it pretty. Okay? If you don't have a translator tool that can reprocess its own output, you can't do that. Most of the translators that exist produce text strings and they're done. You can't reprocess the text string, you're stuck. So you want a good migration, not just any migration. Okay, we'll move on. So I guess the comment is that migrations aren't equal. You can get different answers depending on your technology and what the cost is. Okay, you really want to worry about this. How much does it cost you to live with it? You're going to live with it forever. Okay, that's what you already have. Okay, so it's not a question of what does it cost you to migrate it. It's what does it cost you to live with it. That's the only interesting question.